Good evening, grade 10s, and welcome to our session today on motion in one dimension. And this is a unit on its own that comprises or consists of multiple subtopics. Okay, so we're first going to have a look at frame of reference, position, displacement, as well as distance. Okay, all right, so the first just change my color pen here quickly. A frame of reference. Okay, it has basically the textbook definition is a context against which the motion or position of an object is defined. Basically, a reference frame has an origin. All right, an origin of where it began. Okay, as well as a set of directions. Okay, so instead of putting down all that other mumbo jumbo, let's just get straight into it. Okay, and it's obviously usually represented by x and y axes. Okay, so most of the time you get a question that will often say something such as the reference point. All right, basically a reference point. This is the point, of course, in respect to which we measure distance and position, okay, which is also displacement. I'm going to use this little and sign there of an object. Okay, let's read that again. A reference point is the point in respect to which we measure distance and position of an object. Okay, so that's a reference point. I will have a look at that in a question a little bit later. Okay, now the position, all right, it's horizontal, x, all right, of an object is the point where the object is found at a certain instant in time. Okay, we do measure position relative to a reference point. Okay, so if we measure position that is according to a reference point or against a reference point, we must understand that this word here, position, which I said is also similar to displacement, because in mechanics in grade 10, 11, and 12, we do have what is called a displacement or position time graph. Okay, thus we must understand that a position is a vector quantity. Okay, it's a vector quantity, meaning we must add some direction on it. Okay, now we do define an object's position as positive or negative in relation to the origin. So if I have a look at a quick example here quickly, let's say my journey here is west, all right, and on the other side here is east, and my journey starts here, okay, and I go over here. This is point A, and I go all the way here to point B. I traveled X amount of meters or whatever, and this is obviously in the positive direction usually, because this is my reference point A. This is where I initially traveled from. Okay, this is my reference point. I'm just going to call little r. Okay, then if I now decide that I want to go in another direction, so I want to go back here, okay, and come till about here, which is point C. Okay, my reference point is still point A. Okay, it's still my initial reference point, but now in respect from point A to point C, all right, first we went from A to B, and then did we go from A to C? No, we went from B to C. So now we change our reference point to now determine the position that we are currently in. So obviously now he has gone another X meters, but now he's gone in the negative direction, which is west. Okay, so that's how we determine position. all right, because it's relative to a reference point. So this is my reference point number 2 till I get to C. And if I continue, if I must go from this position in that direction, also x meters again. This is positive. There will be my new reference point number 3. Okay, so that's basically explaining a reference point, and that's how we can define an object's position as either positive or negative in relation to where it originated from. So everything from A to the right, okay, so A is going from A to B is positive, and from C to whatever this point here, maybe this is C to D, that's positive, and anything from B to C going in the opposite direction, that's negative, because we're no longer going in an easterly direction but a westerly direction. Obviously, some people might decide, if the question doesn't say, they'll take from A to B or the easterly direction as negative, and they'll take the westerly direction as positive. But I mean, like, why would you think like that? I often worry about those people, but that's just me. Okay, so usually if an object is right of the origin, we go with positive, usually, which I mentioned, easterly direction. And of course, if it's going to the left of the origin or the reference point, then we know it's basically going in the negative, or the position will be negative. Displacement. Okay, now the displacement of an object is referred basically as an object's change in position. Okay, to put it simply, it's an object's change in position. Okay, but it's considered its change in position from starting point to final position. Okay, so we got to add that in. Okay, it's taken from its starting point to final position. Excellent. Okay, so to further go and dabble with displacement, we have a formula basically called delta x, okay, which means the change in an object's position if x is position. Okay, x is position, like I mentioned earlier on. In fact, let's maybe write that down. So, x is position, the object's position. Okay, delta x is the change, okay, in position of an object. Okay, so basically, therefore, if I have delta x is basically the final position minus the initial position of an object, and that'll give me this definition of a change in an object's position. Okay, it's a vector quantity, okay, that points from the initial position. Now that would be your reference point. Okay, so another way to think of reference point is an object's initial position, okay, to the final position, and it basically represents, in inverted commas, where to of the object relative to its starting point. So where's the object going? All right, where's it going? Okay, now this is not to be confused with distance, which I was going to say for last, but I think it's more fitting to go and just explain it now. Okay, with distance, all right, first of all, it is if delta x is displacement, which is the change in object position, distance is given by the letter d, little d. Okay, and basically distance is actually the length of the actual path an object takes during its motion. So in other words, let's take an airplane. So the airplane flies from Cape Town to Pretoria, or Joburg, or Tambo International Airport. Okay, so from Cape Town straight through to Tambo International Airport, that's got a certain distance. Let's say it's about 1,200 Okay, let's not say 1,200 meters. That's, let's say, about 12,000, for example. 12,000 meters. Okay? Or a little bit more than that. Let's make it 120,000, for example. Let's say it's about 120,000 meters. Which is about 120 kilometers. And it's possibly more than that, but let's just go with that anyway. And then it decides to fly back to Cape Town. So it does, that same plane does about 6 trips. So from Cape Town to Joburg, Joburg to Cape Town back to Joburg, and blah blah blah. So for 6 hours of the day, this airplane is flying. Okay. The distance would be from Cape Town to Joburg, Joburg back to Cape Town, and Cape Town back to Joburg, and Joburg back to Cape Town 6 times in total. So basically 120,000 meters added up 6 times. That'll be the distance, which is the actual length. So the total distance that the plane flew would be that the same trip times by 1 times by 6, right? The total distance that it covered. However, the displacement would be different. Okay, so displacement of from let's say from Cape Town to Joburg, that's its first flight. So xi would be Cape Town and xf would be Joburg, the final position minus the initial position. Okay, so that'll be whatever the position was from here to there minus so Joburg is 120,000 meters away from Cape Town, and then it flies now back to Cape Town. Then obviously it'll be 120,000 meters minus 120,000 meters gives you 0. In other words, it's now back in its initial, or it's back in its initial reference point or frame of reference, because it's now back in Cape Town. So displacement is now 0. But if it went from Cape Town to Joburg and then from Joburg to Durban, it's now changing directions all the time. It's going in different directions. So we'll show you an example how we would calculate displacement by actually taking the initial or the final position minus the initial position. But with distance, we don't do that. We just add up the total length of the motion of the entire object. Okay, it's a scalar quantity. Okay, it's a scalar quantity, so it has no direction. Okay, that's the difference between distance and displacement. Okay, hope you got my little airplane example there. Let's just take that distance example quickly. Okay, and this is one-dimensional motion that I'm about to do now. Which is worth just mentioning, but basically one-dimensional motion is motion of an object along a straight line, okay, which you see here. It's about a straight line, okay, and we just take this to be the x-axis, okay, that does have an origin. So let's say here is home, okay, and here is school. Okay, now the entire distance from, let's draw it a bit at the bottom here, from home to school, let's say that is about 100 meters. Okay, now that's 100 meters just from your home to your school and from school back home. Okay, so let's say you come along, okay, a little long hair there, okay, maybe just add a couple of more strands so you don't look like you are, you know, going bald. Okay, there you are. And now you decide, okay, cool, you're going to walk in this direction. Okay, so now you walk. Okay, cool. And then you stop here at the shop because you want to buy some gum or whatever. And this was maybe 20 meters. Okay, cool. And then you end up here. This is point A. Then you actually end up at point B. Now you're walking back to school, but now you decide you want to walk here. Let's use another color. And now you walk here, and this is, I don't know, this is Jordan's house. Okay? And now this is 50 meters from school. It's not exactly 50 meters because halfway is like here, but we'll say it's 50. Or let's say it's 40 meters from school. Okay, And then you decide, oh flip, I left something at school, so now I go back to school. So now you go 40 meters again in this direction, and then you come back another 40 meters again, pass now, or you get back to Jordan's house, and then you walk the rest of the 60 kilometers back home. Okay, so your distance, okay, now let's make it little d, is equal to the 20 kilometers that you walk to the shop, okay, plus the 80 kilometers that you walked from the shop to school, plus the 40 kilometers that you walked from school back to Jordan's house, plus the 40 kilometers that you walked back to school, plus the 40 kilometers that you walked back to Jordan's house, plus the 60 sorry, I'm using kilometers instead of meters, plus the 60 meters back to your house is going to equal to the total amount of meters or distance you have just trapped for the entire day. Okay? Make sense? To everybody? Yes or no?
Yes.
Okay, cool. So let's add it up quickly. That's 100. That's 100. 100 already. 200. So you walked about 280 meters for the day. Okay? But now, when it comes to displacement, delta x is slightly different. So you got 20 meters. So that's positive 20 meters because this way is your positive direction. So you got positive 20. All right? Plus positive 80. Okay. Then now minus 40 meters. This one. Plus 40 meters. This one. Minus 40 meters. This one. Okay. Minus 60 meters. Back home. Back to point A. That will give you your delta x. Okay? So, you must work this out. Positive 20 plus positive 80 plus or minus 40 plus 40 minus 40 minus 60 gives you 0. Because you've ended up back home. So your position hasn't changed. In other words, you have not ended up walking technically, or in terms of your position hasn't changed relative to A, because you are back at your initial position. If you had ended up past point A, if point C was past your home, maybe at your uncle's house or something, or if point C where you stopped was maybe Jordan's house, then we'd have a different story. Okay, then we would still have a position, and let's check. So now let's say our initial position stopped, we didn't walk 60 meters home, we stopped here. Okay, let's take all this away. Let's say we stopped there. Okay, so in other words, that's 20 meters to the shop, bought our gum, walked the 80 meters, then to school, then walked back, stopped at Jordan, this is to Jordan, then went back to school because we left a book in our locker, and then we came back to Jordan's place and we ended there. So we check that out. So we got 20 plus 80, which is 100, minus 40 plus 40 minus 40. We end up with 60 meters, and it's still a positive number, so 60 meters east would be our change in position from, because this was point C here, from point A, right? That's our change in position. We're still 60 meters away from home in the positive direction. All right, we'll look at a bit of a more in-depth or a more practical example, okay, in just a momento. All right. All right, ladies, so what I do have is the same chapter open in the Siavula textbook just to have a look at the distance versus displacement notion that I just explained earlier with my little skeleton made-up example. Okay. Here we've got a situation where Kamal walks to meet Kevin, all right, at his house before walking to school. Okay, so you see Kevin is just before the shop. Okay, and what is Kamal's displacement, and what distance did he cover if he walks to school via Kevin's house? All right. So first, so we can clearly see that there's the motion in one dimension, a little line there, which is a straight line we can see, is in 100-meter intervals. All right. So Kamal's house is 100 meters away from school. All right. And now basically, if you look here and you want to add up, basically that's 100. Then that's obviously 200, 300, 400, 500, and 600, etc. Okay. So now we need to find out from his house. And that's one. So that's 1, 2, 3, and 4. So Kamal covers a distance of 400 meters to Kevin's house. Okay. And now he's got to go back to school now. So that's another 1, 2, 3, 4, and 5. And another 500 meters from Kevin's house to school. Okay. Silly boy. All right. Kevin could have met him at his house. Anyway, but he decided he was going to go to Kevin's first. Okay. He covers a total distance of 900 meters. Now, if you check at the sum here, basically distance is your path traveled. So it's just 400 plus 500 gives you 900 meters. But your displacement, all right, is only 100 meters. All right. Because displacement only looks at the starting position of his house and the end position, which is his school. All right. That's all. Okay, it doesn't depend on the path really that he has traveled. So if we take here, clearly we can see that the reference point that they have chosen is Kamal's house, and towards Kevin would be positive, and towards the school would be negative. So the position, which is school, is 100 meters, but it's to the left of his house, or in a westerly direction. Okay, so that's negative 100 plus 0 or minus 0 meters. Okay, doesn't really, that actually should be a minus. Okay, and if we end up being minus 100 meters, which basically means it's 100 is displacement from the school from his house, displacement is 100 meters in the negative direction. That's all. That's all is his displacement. Okay. So if you get a negative answer here, it's not that your answer is wrong. That's obviously just determining your direction. Okay. Hope it all makes sense with this little example. We're going to have a look at a more practical example in just a second. So this little table is very important, girls, is that the differences between distance and displacement can obviously be summarized into tabular form. One, distance depends on the path that you travel, which displacement is not dependent on that. So it's your position, your initial minus your, or final minus your initial. Your distance will always be positive, but your displacement can either be positive or negative depending on the direction that your final position is from your initial. And distance is a scalar, while displacement is a vector. Okay. Now we have a little exercise here, and what we're going to do, we're just going to do number 1. Okay, so number 1, I'm going to let you guys have a look at it, and then I'll read through it when we come back and have a look at the answers. Alright, Kogis walks to Cosmo's house and then to school. What is her distance and displacement? Okay, so easy thing to do is obviously to calculate distance first. Okay, so we got D, alright, this is for A. So D equals 2. If we take where she is, she walks to Cosmo's place. So that's easy. And then to school, what is the distance? So first, she walks 100 meters, and then from to school, there's another 1, 2, 3. So that's basically 100 meters plus 300 meters gives you a distance of 400 meters. Okay, but now her displacement. Okay, so if we take where she is, all right, so 1, 2, 3, 400, okay, is basically where she is, and the school is 400 meters away from her house. Okay, so displacement would be a final position, all right, minus her initial position. So initial position is obviously a 0 point or a reference point. So we have xf minus xi. So final position is school, which is minus 400 meters away from a house. Okay, and that's also minus 0. All right. Okay, the reason why we saw it was plus 0 is because it's a frame of reference and 0 is a positive number. So I'm going minus 0 because it's a positive number anyway. So it still gives us negative 400 meters, right? Which is basically 400 meters in the negative direction. Okay, so that's the difference there that we got there. So that was for A. Let's have a look at B. B is the same type of question. B says now that Kolo walks to Cosmo's house and then to school. So Kolo's over here, and Cosmo's house is 100 meters away from him, so he walks 100 meters. Here we go. And then from here, 1, 2, 3, 4. So entirely, he walks 100 plus 400 makes it 500 meters. But now his displacements, if you take his house reference point, so that's 0. School is 1, or school is 1, 2. So we have xf minus xi, which is minus 200 minus 0, and that gives us minus 200, of course, which therefore gives us 200 meters in negative direction. Are our answers looking more or less like what we see on the screen here? Yes or no? C, now Kamal walks to the shop, okay, and then to school. What is his distance? Kamal's over here. Okay, now his displacement is still the same as the example here, but his distance now, he walks now past Kevin's house. So he walks, well, 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5, 6. So his distance starts out by walking 500 and then another 600 meters. So he ends up walking about 1,100 meters in total. But his delta x, of course, is taken from his reference point. So xf minus xi, which is basically the school is 100 meters away from his house, if you're taking his house as reference point. Okay, so that is basically negative 100, which equals 100 meters in the negative direction. Okay, and that was it. And then D asked us to what reference point did you use for each of these questions? Okay, well, I think from A to B we used, of course, the A to C. We basically used the students' houses. Okay, you can either say students or learners' homes or houses as their point of reference. Hope that makes sense. All right, that was that. All right. Okay, so here we got a little bit of an exam paper here from November 2018. I had 2017 open, but that was a question that wasn't so well phrased. They were asking it more from an average speed point of view, and I just want to test what I've taught in the past 2 weeks, or last week and this week, which is vectors and, of course, vectors and scalars, and now motion in one dimension. So this is one of those questions. This question 2 says a baby leaves a bowl of food on the floor and crawls west to to fetch a toy that's placed 5 meters away. At the same time, a dog walks eastwards towards the baby, and it takes the baby 30 seconds to reach the toy. The dog walks past the toy to eat the baby's food in the bowl, like a typical dog would. Define the term displacements in words. I'm not really worried about that. Determine the position of the dog relative to the baby before they moved. Now, that's a good question. I know 2.3 and 2.4 is ask us to calculate average speed and velocity. Don't worry about that. That's okay. But I'm interested in 2.2. Okay, and 2.1, of course, you can define as well. But 2.2 says now determine the position of the dog relative to the baby before they both moved. All right, 2 marks. All right, let's see if we can go ahead and do this. Okay, 2 marks. So in about 2 minutes, I'm going to take some answers, and then we're going to go and check what the right answer was. Okay. All right, let's see if we have an answer from the girls. Determine the position of the dog relative to the baby before they both moved. Okay, do anybody have some answers? Anybody have some answers? Relative, the position of the dog relative, all right, to the baby before they both move. So we see a baby that's 5 meters away from the toy, and the dog is 7 meters away from the toy, but they're both in other directions. And we can see we have a compass there to determine north, south, east, and west. And because we're doing one-dimensional motion, we're only concerned with west and east, or east and west. Okay, not really north and south. So did everybody have an answer? Okay, because we've got numbers there, but can we at least determine the direction? Okay, I will wait for an answer. All right. So, I actually can't remember if I recorded the answer to that previous question that we saw. But the answer to the previous question was 12 meters west. Okay, for 2 marks. All right. The reason why it's 12 meters west is because the baby was 5 meters away from the toy, and then the toy was a further 7 meters away from the dog, and the dog was on the opposite side. So the reference or point of reference was the baby, and so with using the same compass directions that we see on our current screen, the dog was 12 meters, 5 plus 7, but it's 12 meters west. So in other words, negative 12. The negative there displaying the change of direction, or in the negative direction, meaning the west direction and not east. East we took as positive. Okay, now over here, unfortunately, they don't really exploit the vectors, and they don't really exploit the motion in one dimension reference point questions in grade 10. They like to exploit the average speed and velocity questions a bit more, but in grade 11 they do stress more the actual vectors and scalar or more vector questions, because in grade 11 you do vectors in 2 dimensions. Okay, we've only up until now done vectors in 1 dimension, but in grade 11 you do vectors in 2. So they do exploit that a little bit more in grade 11, unfortunately. But here's a question, I think it's from 2017. A brother and sister walk home from school. After walking 500 meters eastwards, the brother realizes he left a book at school and returns to school. His sister continues walking another 800 meters to their home, and she arrives 30 minutes after leaving school. Okay, so possibly the brother could have possibly arrived home after about another, I would say, close to an hour of walking, because if 30 minutes was from about not where not the position from where the brother turned back, but I think if I'm reading this question correctly, after 30 minutes after leaving school is from the time they left school, or she left school, all the way home. So brother probably took about just more than an hour, probably, because already walking about 500 meters, that's obviously some time, and then going back there and then back, so probably more than an hour to get home in terms of time. But that's not really important. That's just me making sense of the question for me. Okay. So the question that I want to focus on, if I just zoom out slightly, is question 2.3. Okay, I'll make that about 85. It's question 2.3, which does say use a vector scale diagram and represent the displacement of the boy from the time he realized he left his book at school until he reached home. Include all relevant information in the diagram. So this is a normal vector diagram, okay, that we learned last week. Use the scale 1 centimeter equals 100 meters for the diagram, okay, and that's for 3 marks. Okay, so let's take our time, about 3 minutes, and let's draw this diagram, and then we'll mark it. All right, so let me just there we go. So of course, from the point that he realizes that he forgot his book at home, at school. So let's draw a little point here. And of course, 1 centimeter equals 100 meters. So 5 centimeters, roughly, I'm just going to, I don't have a ruler here. So in that direction, that's 500 meters. All right. And then he further has to go, of course, another 800 here. Okay, there we go. So that's about 8 centimeters. All right. And then, of course, when he returns here, okay, or let me not draw that part next, actually. Let me just take that out. Let me rather do this. I'm sorry. I'm sorry. So, basically, they told us to include everything that we needed for the question. Sorry, guys. There we go. So, include all relevant information in the diagram. So now he's at school over here. You make this line a little bit more, dot a little bit more accurately in line here. So I'm just going to draw a bit of a dotted line. I'm going to include it here. So now he gets to the school after here, realizing that, oh, flip, I left my book at school. And home is over here somewhere. And now he walks all the way back here. Straight home. Okay? Which is over here. With this little arrowhead. Okay. So, obviously, if the sister carries on, okay, just drawing her little journey here as well. Okay. So she comes till about here. Okay, so this obviously is the 800 meters that he also still covers. So 500 back to the school, and then from school all the way back, which this would be home. This is all in total 1,300 meters. Okay, which is very evident from the diagram as well, because here's 500 and there's another 800, so that together is all 1,300. Okay, now what he does is he goes all the way from this point where he realizes, ooh, flip, my book, back to the school, which is 500, and then from the school walks the entire 1,300 meters, which he would have only have walked if he did not forget his book at school. And of course, therefore, he also covers the same 800 meters that his sister did, of course, in his journey as well. So that's how your diagram, vector diagram, should have looked. You didn't have to include this or these little dotted lines. These were just for me to make sure I draw them straight. So I'll take them out for you. Okay, just get them out. There you go. Just neaten up my lines here slightly. Okay. So that's how it should have looked. And that's my presentation for this evening, grade 10s. Thank you so much for joining me. Please stay tuned for the next video series. We will be having a look at average speed and average velocity.